All right, example 3 for studying concavity of a function. We're good to determine the domain, concavity, and inflection points for this rational function. All right, let's start with domain. The domain is where it's undefined. We have to exclude those values, and we do have a denominator where there could be zeros. So when is x squared minus 3 equal to 0? That would be at plus or minus rad 3. So the domain is all real numbers. But we do need to exclude those undefined values. So except x equals plus or minus square root of 3. All right, so there's our domain. Concavity. All right, so we need that second derivative. I'm going to start off with writing h of x as a power. So in other words, that would be x squared minus 3 to the negative 1. Now I'm going to do it that way for this one iteration. However, you could do this as a quotient rule. That would work. All right, so if I put it in this form, I'm going to use a power rule. So h prime of x. Using the power rule, my base is this quantity. So the power rule would be negative 1 times my base, which is x squared minus 3. And then I subtract 1 from my exponent, which is, that would be negative 2. Then I have to use the chain rule and multiply by the derivative of the inside, which is 2x. And I'm going to rewrite this as a fraction. So that's negative 2x in the numerator. And then that quantity will go in the denominator. Now I need to take the second derivative. All right, for this iteration, I am going to use the quotient rule. So derivative of the numerator comes first. So that would be negative 2 times the denominator. Minus, and then I keep the numerator, negative 2x. And then I multiply by the derivative of the denominator, and that would be a power chain rule again. So that would be 2 times this quantity to the first power. So 2, so times 2 times x squared minus 3 to the first power. And then times, and then I take the derivative of the inside, which is 2x. And then divide by the denominator squared. So this square would be to the fourth power. And I'm going to start to do some simplifying. I do notice that all three of these terms, so this first term has an x squared minus 3 factor. The second term has an x squared minus 3 factor, and the denominator has an x squared minus 3 factor. So I am going to divide the numerator and the denominator, or multiply by 1 over x squared minus 3, 1 over x squared minus 3, and distribute that. And so what effectively that does is it cancels one of these factors for each of the terms. So this factor gets reduced to the first power. This factor gets reduced to the 0 power, and so in other words, it's just gone. Multiplying by 1 over x squared minus 3, this is just gone. And the denominator multiplied by this leaves me with this to the third power. So I reduced all of those down. It's convenient. And now I can just simplify the rest. So this is negative 2 times this quantity to the first power. That means I get to distribute it. So that's negative 2 x squared. And then negative 2 times negative 3 is plus 6. All right, and then in this quantity, remember that this term is now gone. And not only that, I just noticed that I have this double negative. So this will be positive. Kind of simplify that part. So all I have to multiply is a positive 2x. This will be plus positive 2x times 2 times 2x. So that's going to be 2 times 2 times 2, 8 and then x times x, x squared, 8x squared. And then all divided by the denominator, so this base x squared minus 3 to the third power. And then I could rewrite this one more time. So this is my h double prime of x. And I'll just simplify the numerator a little bit. So combining these two like terms, oh, it isn't, they aren't like terms. Oh, what did I mess up? I see it. I said x times x, but I wrote x cubed. That should be x squared, right? You guys catching it? Okay, so 2 times 2 times 2 is 8, x times x, that should be x squared. And then we have two like terms. If I combine 8x squared minus 2x squared, that's 6, x squared positive, and then plus 6, all divided by x squared minus 3 quantity cubed. All right, so this is my second derivative. Now to figure out concavity, I need to find out where it's equal to 0 and or where it is undefined. So to be equal to 0 is where the numerator is equal to 0, but there are no zeros for the numerator. Do you know why? Well, there's what possibly could make this 0. This first term is positive, and adding to that another positive, there's no way that will ever be equal to 0. So, or you can set it equal to 0 and then work through it, and you'd see there were only complex roots. So there are no zeros for the numerator. Therefore, the second derivative will not equal 0, but the denominator we already learned could be 0 when x is equal to plus or minus rad 3. So those are going to be the values that we will test around. However, I am going to note that they cannot be inflection points because they are not in the domain. So they will be vertical asymptotes for the function, not points. Even if the concavity changes, it doesn't matter. It has to be a defined point. So I am going to make a number line test. And testing h prime, right? So we're going to look at h double prime. And we're testing around those two roots. So I have negative square root of 3. And I have positive square root of 3. And I want to see how concavity changes around those two values. So I'm going to test a few values. I'm going to pick some numbers in between. So let x, how about, so this is about negative 1.7. So what if we chose negative 2? And then in this middle interval, I'll pick x equals 0. And then to the right of square root of 3, a number would be 2, positive 2. So I'm going to test those three numbers with h double prime. All right. So if I substitute in negative 2 into this, all right, so remember that we're plugging it into this function here. All right, so if I put negative 2, so h double prime of negative 2. All right, in the numerator, this numerator is always positive, right? We're squaring negative 2, multiplying by 6, adding 6. So the numerator is always positive. So that was easy. And then the denominator could be negative because if you cube negatives, you get negatives. So we need to figure out if it's positive or negative. So if I put in negative 2 here, I'm squaring that. That will be 4. 4 minus 3 is 1, which is positive, and I'm cubing that positive. So I get a positive in the denominator, which means that my second derivative is positive. So this is positive here. Now I test 0, so h double prime at 0. All right, so putting in 0 into the numerator, I get 0 plus 6, which is positive. So the numerator is always positive. And the denominator, I would do 0 squared minus 3. Well, that would be negative 3. And cubing that is a negative. So that's less than 0. And so negative in the middle interval. To the right of rad 3 is 2. So h double prime at 2. And we're going to get a similar result as we did with negative 2, right? Because in both cases, we're plugging those numbers into the square. So this is going to be positive in the numerator. Denominator is 2 squared, which is 4, minus 3, which is 1, which is positive. All right, so greater than 0. And so now I can make my conclusion. So H is concave up on the intervals. There's 2 intervals. So on the intervals from negative infinity to negative 3, root 3, combined with union with the interval from square root of 3 to infinity. And then we state a reason because the second derivative is positive. So we can just say H double prime is greater than 0. And H is concave up on the interval from negative rad 3 to square root of 3 because F double prime is negative or less than 0. Oh, not F, it's H. Okay. Now, inflection points. I know the concavity is changing around negative rad 3 and root 3, but again, remember, to be an inflection point, you have to be a defined value of the original function, and those are not, the function isn't defined at those values, so there are no inflection points. H has no inflection points. Okay. All right, so we're done. We've got concavity, inflection points, check, done. All right, let's take a look at example 3. All right, so I think I'll stop there and we'll do another video with the last example.